Welcome to Lesson 12 on combustion reactions. So let's start with a brief introduction. Okay, so when we think of combustion, we often think of burning things. So here we have a video of these matches, right? And we're about to light these matches. This is a combustion reaction. It releases heat. Okay, now some characteristics of a combustion reaction as these are going. Characteristics. The first major characteristic is it releases heat, and we call that exothermic. And it's got a change in heat or an enthalpy that's less than 0. So the delta H value for this is negative, or it's seen on the product side of the reaction. Okay. One thing you're noticing here right now is these matches are burning spontaneously. They're just burning on their own. So combustion reactions are spontaneous, meaning their delta G, much like batteries, is less than 0. Okay. Now this is weird because you had to actually start it with the match. So a reaction that's spontaneous might not happen visibly until you initiate it. Okay. So that's a key thing for combustion reactions, and that's really why we don't have things like spontaneous combustion, or I'm not like burning right now even though I'm surrounded in oxygen. They have high activation energies. We can call that the EA. So if we look at an energy diagram for a combustion reaction, I'll move to red here. If we spot energy or plot energy here, sometimes they call that potential energy, and just the reaction coordinate. So this is just the reaction happening. The reactants start here, and the products always end lower. So if this is the reactants and this is the products are ending lower to indicate that it's an exothermic reaction. And that difference between the reactants and the products, that's delta H. Okay. Now, if this just went directly like that, okay, these reactions would be really dangerous. Things would just combust naturally. Okay. But combustion reactions have to achieve a certain amount of energy before they happen. Okay? And this energy here, that's the activation energy, or E sub A. So we can think of this region here as like energy in, okay, and this here as energy out. And in a combustion reaction, the energy out is always greater than the energy in. So a reaction can be spontaneous, but not really happen visibly until it's initiated. So a spontaneous reaction is one that happens on its own after it's initiated. Okay. So the driving question that we're going to use here for this, our driving question for all combustion reactions is how much heat is released. This is our driving question. This is really the only, this is really the only question that we are trying to answer for this cycle. How much heat's released? So let's look at a generic combustion reaction. In a generic combustion reaction, we have something that when reacted with oxygen produces something else as well as heat. Now, we tend to think of combustion reactions as things that contain carbon, some amount of carbon, hydrogen, some amount of hydrogen, and some oxygen, maybe. And we tend to think of those things as reacting with oxygen to produce CO2 and water. That's one type of combustion that we deal with usually in motor vehicles. But notice, it is the red components, the reactant oxygen and the production of heat, as well as a fairly high EA here to make this happen, that are the characteristics of combustion reactions. So how much heat is released? And there are two ways of figuring that out. We're going to learn both of those. So technique number one is called calorimetry. Both of these techniques are exceedingly easy. We just got to keep track of them, okay? So in technique number one, we are going to understand that a combustion reaction reacts with oxygen to produce something else and heat. Oh, sorry about that. Plus heat. And what we're going to do is we're going to take this heat and we're going to use this heat to heat up something else. Usually water, but it doesn't have to be. Okay? And this technique, how much this thing's temperature changes, okay? We'll call that its delta T. Its T final minus T initial can lend insight into the heat that was released. Okay? So when we do it this way, we call this calculation Q. Okay? And this substance here not only has a change in temperature, it also has a mass, and it also has C, its specific heat. Okay? The specific heat is how hard it is to heat it up. So for example, if I was heating up some water, water has a lot of hydrogen bonding in there, so it's fairly hard to heat up. But if I was heating up something else that maybe like alcohol, alcohol has one less hydrogen bond. So its C is going to be less. So we have a stepwise process for figuring this out. The first thing we do, step 1, is we calculate Q. So Q equals the mass of the substance multiplied by its specific heat multiplied by the change in temperature. And that's going to give us an answer in joules, okay? So the heat released from the combustion reaction is going to be used to heat up water. The mass of the water, the specific heat of the water, or the change of temperature of the water gives us the joules, okay? Step 2. When we get this value for delta H, that value is going to be in kilojoules. So we want to take our joules and we want to divide it by 1,000 to be equal to kilojoules. Okay. And step 3, the units on the delta H that we eventually want to get are kilojoules per mole of the reactant. So what we have to do is take those kilojoules and divide it by the moles of the reactant. And that's technique number 1. And it's really, really useful. You can take any combustion reaction and literally contain that heat and heat up something else. We get Q, we convert Q to kilojoules, and we divide that by the moles. Let's look at the problem. So let's say we have a propane barbecue, C3H8, and we're combusting it. Okay, so the combustion produces CO2 and H2O. Now, just good chemistry etiquette is to always balance these reactions. And it's producing some heat. But the question here is how much heat? Now remember, the units on this value need to be kilojoules per mole. Okay. And it gives us some data. Okay. It says we heated up 60 grams of H2O. Okay. And the water went from 25 degrees Celsius to 100 degrees Celsius. And the C for water is 4.13 joules per gram degree Celsius. So we're going to use calorimetry. Let's go through and do this. First step, Q equals MC delta T. So that equals 60 grams multiplied by C, 4.13 joules per gram degree Celsius, multiplied by T final minus T initial. So this is 75 degrees Celsius. Now, look at how these units really work out. The grams cancel and the degrees Celsius cancel. And I'm left with joules in this case. Okay. So my joules here is going to be 181.35 joules. But we want it in kilojoules per mole. So let's do step 2. Kilojoules equals 181.35 joules divided by 1,000. That's going to be 18.135 kilojoules. Okay. But they want it in kilojoules per mole of this. So I didn't give you that piece of information, but let's say we had 22 grams of C3H8. There are 44 grams per every 1 mole. That equals 0.5 moles. So we take our 18.135 kilojoules. We divide that by 0.5 moles, and we arrive at our final answer, which is going to be 36.27 kilojoules per mole. So how much heat was released? Plus 36.27 kilojoules every time you had 1 mole of C3H8 combusted. That's technique number 1. Technique number 2 is really nice, and this technique is using bond energy. This is more of a technique that requires a table to do it. Okay? But let's go ahead and let's look at our standard combustion reaction. So something plus O2 goes to something plus heat. And the question again is how much heat? So in the past, what we did is we heated up some water and we did Q equals MC delta T. That's calorimetry. We're not going to do that this time. Now what we're going to do is we're going to understand that the reactants bonds are broken. And any products we make, those bonds are formed. So if we look at it in terms of an energy diagram, remember this is energy, and this is just the reaction coordinate or the reaction happening. And we start off here with the reactants. Those are these fellas right here. They're going to achieve some activation energy, E sub A, to form products. Now, they're not going to stop here. It's a combustion reaction, so they're going to go down. Okay. And this here is the delta H we're looking for. Now, we learned that we could get that delta H using calorimetry, but we're not going to do that. We're going to get that delta H using bond energy. So I said earlier that this is energy in and this is energy out. Well, let's look at it in a different way. Here, bonds are broken. When all the bonds are broken, we've accomplished our EA. We've gotten to the top of that hill. EA! Yay! Woohoo! EA! So weird. And when we turn over that hill, bonds are formed. Okay. So if the bond's broken equals the bonds formed, then the up is equal to the down, and delta H in that case equals 0. That's not what we're doing for a combustion reaction. If the bonds broken are greater than the bonds formed, the energy of the bonds broken, then we actually end up higher, and that would be an endothermic reaction. And we're not dealing with that either. But if the bonds broken require less energy than the energy you get when the bonds are formed, okay, then delta H is less than 0, and this is what's characteristic of combustion reactions. Okay. Let me give you this equation in a little bit of a simpler fashion. Delta H is equal to the sum of, okay, the delta H for the bonds broken minus the sum of the delta H for the bonds formed. And that answer is going to be in kilojoules per mole. So unlike the calorimetry problem, you do not have to go about doing a problem where you actually convert to kilojoules per mole. So before we do an example, let me show you some techniques here that we do it. So let's take the combustion of hydrogen. And when we balance it here. Okay. So the question here in this problem is how much heat. And they do not give you calorimetry calculations. We're going to do it bond energy-wise. So when you do it bond energy-wise, the first thing you do is you draw the Lewis structure for each reactant and each product. And you keep the coefficient there. So 2 there plus 1 oxygen goes to 2 waters. Now you don't have to worry about shape or lone pairs. All we care about is the bonds. So in this case, 2 of these hydrogen bonds are going to break, and 1 of that oxygen bond is going to break to make water molecules. Okay, so we make 2 OH bonds 2 times when we do this. So let's look at how the delta H would look. The delta H is going to be the sum of the bonds broken. So let's do the bonds broken first. Here we have 2 of this value. You're going to get this value from a chart. Let's call that X. Plus 1 of that value. You're going to get it from a chart. Let's call that Y. Minus 2 of the OH value. You're going to get that from a chart. Z. And that, my friends, is happening 2 times. So really you have 2 OHs, but you have 4 of that. So you're literally, this is going to be a number, this is going to be a number, this is going to be a number, that's going to be a number, and what's going to come out is kilojoules per mole. And it's usually going to be a negative value. Remember, the negative is just telling you that heat is released. So let's look at an example of a problem that showed up here. So we have this reactant. They went ahead and gave you the actual Lewis structure for it. That's legit. And we have these products. And they gave you the bond energies here. Okay. So we'll get to see in a sec, but it says based on your data, calculate the kilojoules per mole, or the delta H. So we know that this problem here may be releasing or absorbing heat. We don't know, but we don't have calorimetry data. So let's go ahead and do it this way. Delta H equals the sum of the bonds broken minus the sum of the bonds formed. So we know that the reactants are broken, and we know that the products are formed. If the broken is greater than the formed, it's endothermic. If the broken is equal to the formed, delta H is 0. If the broken is less than the formed, then it's exothermic. Okay. So broken here, we have 1 CC bond. Okay. So that 1 CC bond is right here, and its value is 348. So I use that, I'm going to get rid of it. Okay. Plus, we have 1 CN bond. CN bond is 293. We're going to get rid of that. Okay. Here I have 2 NH bonds. So 2, the NH bond is 391. Okay. There it is. Plus 1, 2, 3, 4, 5. 5 CH bonds, which is 413. Okay. That takes care of all of the bonds that were broken. That's how much energy it takes to break those bonds. Let's look at the bonds formed. Okay. First off, I have a C double bonded C. So 1 C double bonded C is 614. Took care of that. Then I have 1, 2, 3, 4 CHs. 413. And then I have this molecule here. 1, 2, 3 NHs. So all you do in this problem is you simply add this up. You're going to get a number, and you're going to subtract it from this number. Okay. I'm not going to go through and do this right now. It's just an example, but your answer is going to be in kilojoules per mole. Okay, so it says, based on your answer, predict whether the temperature of the contents of the insulated container will increase, decrease, or remain the same. So if delta H was 0, they'd remain the same. This is delta H equals 0. If delta H was greater than 0, it would decrease, and if delta H is less than 0, it would increase because it would actually release heat to the surrounding environment. Okay. So your multiple choice problem, I want you guys to press pause and look at this problem. Okay. So it says, according to the data in the table below, what is the value of delta H? Okay, so we have delta H. We have two ways of getting it. One is calorimetry, how much heat's released by increasing the temperature of some substance, usually water, and the other is bond energy. And we know right away when looking at this problem, it's going to be bond energy. Okay. So remember, draw the Lewis structures here and go through it. And I want you guys to write a summary. So what was this video about? What did you understand? What did you struggle with? And what questions do you still have?